welcome you all to this advanced control system design for aerospace applications. So, this particular lecture will be about giving an overview of the entire course, followed by the motivation and the objectives of this course, motivation for this course and all that. Once you are ready with the proper motivation, and all our learning becomes easier. So, let us see first what is our objective here. First objective is to study the concept and technique of linear and nonlinear control systems. Both linear and nonlinear will be covered here in this particular course, and then it will have some preferential emphasis towards aerospace applications. That does not mean that it is completely aerospace. We will have lot of examples which are also generic. That means, the concepts and mathematical formulations and all that we talk here will be in the generic formulation. So, even though there is some emphasis towards aerospace applications, all other applications can also be very well within the course material per se. So, the topics covered or roughly the syllabus part is something like that. We will first talk about introduction and motivation, which is roughly the course material today. And in other words, this particular class will talk about some sort of giving an overview along with proper motivations. Then we will talk about some overviews of first and second order linear ordinary differential equations, typically what are covered in undergraduate courses. And some of those will be like that, the entire course is geared up towards like that. So, the next set of topics will be overview of Laplace transform, and then transfer functions, what we normally study in undergraduate courses. Then we will talk some overview of classical controls techniques. In other words, it will not be entirely exhaustive, but some sort of overview of the classical control techniques, just to get ourselves ready for modern control. We will try to appreciate more once you have some fundamental knowledge or basic overview of classical control systems also. So, once again it is not going to be a full overview of entire classical control, but just some sort of important topics for classical control. Then on the way we will also introduce this flight mechanics and flight control system overview. So, remember this is a aerospace related course. In other words, we have some preferential emphasis for aerospace control systems. So, understanding the basic flight control systems and flight mechanics is also part of this course. So, we will not devote too much of time, but especially 1 or 2 lectures we will devote on the way. Then we will go a little more serious, then talk about how about state space representation of dynamical systems in general. So, more or less it is again nowadays become undergraduate material. However, we will review that and then we will move further on that. We will talk little more depth compared to what you really learn in undergraduate subjects. Next, we will talk about linearization of nonlinear systems, because there are, as I told in the beginning, this entire course is geared up both linear as well as nonlinear systems. So, we will see how we talk about linear. Before we talk about linearized methods or linear control designs techniques, we need to know what is linearization process. So, we will probably talk about, devote one lecture for linearization of these nonlinear systems, especially since most of the real life systems are nonlinear anyway. So, it makes sense to study that in a little more depth. In other words, given a nonlinear system, how do we find out a linear approximation of that system around an operating point and all will be that topic will be covered in that lecture. Next, we will talk about some review of matrix theory, which is a key component of modern control systems. It will be fairly exhaustive. I will not talk about all sort of theorems, proofs and all, but at least important concepts along with some degree of important results and some degree of a little bit examples and all will study on the way, which will help us understanding the linear system control in a much better way. It is also useful for nonlinear control system design anyway. So, that is how it is put there. Then we will have a quick review of numerical methods in system engineering. As we do research or do more on nonlinear method, linear method, all sort of things, especially nonlinear control design techniques, we also need some numerical methods as our tools to talk about especially nonlinear control design techniques. So, it makes sense to have a quick review of numerical methods, what is typically useful in systems engineering. Next, we will talk about dynamical systems time response, and this time we will be talking in terms of state space form. So, if you given a state space form of the system dynamics, how do we really come up with this time domain solutions from a set of initial conditions? So, that's what we are interested in this particular topic. Next, we will discuss about stability, controllability and observability, which are very critical for linear systems analysis. Some equivalent concepts are also there for nonlinear systems in a limited way, but we are not going to talk too much on those aspects. But for linear systems, clear cut results are available. So, we will be able to discuss in a very precise and clear way for linear systems. So, that is what the motivation here. Next, we will discuss about a specific control design technique called pole placement. This is especially useful for linear system design. The same technique can also be used for designing observers. So, that will also be a part of the course. Next, we will go to some quick overview of optimization and optimal control. So, one lecture will be for optimization only. So, parameter optimization, static optimization essentially. Next, we will talk about how do we extend that for or how do we kind of formulate control design techniques from optimal control theory point of view. Here, we will need some sort of variational calculus approach. So, that will be part of one lecture probably. We will see as you go along. But mostly in one lecture, I will be able to summarize the important concepts there for optimal control, which will subsequently be used for what is known as linear quadratic regulator design. And there we will spend about 1 or 2 lectures to kind of give a good overview of what is LQR design really. Next, we will see applications of all these linear control design techniques to autopilot design of aircrafts and missiles, which is again we will kind of tie it up together for the concepts that you read to the applications that we have in mind, which is essentially aerospace engineering. Next, we will talk about nonlinear control design philosophies, and there the first thing comes to mind is what is called as gain scheduling. In other words, you design gains for several operating points where you have different gains for different, you select different operating points around which we found out some sort of a linear approximation. We design specific gains for all those all those operating points, and then we tie them out or we stitch them up through some sort of interpolation routine. So that interpolation will kind of give us some sort of a nonlinear control design called as gain scheduling. So, we will talk about that in a quick overview sense. Next, we will move on to what is called as dynamic inversion design, where it essentially attempts to eliminate the requirement of gain scheduling. Because gain scheduling becomes a tedious process, it becomes problem specific. Suppose the problem changes, next time you have to repeat the exercise again, all sort of problems being there. There are attempts in current literature to get away from there, and that one way of doing that is going into this dynamic inversion design. We will also talk about this particular design in detail in couple of lectures. Next, we will move on to the stability analysis of nonlinear systems using Lyapunov theory. As we kind of appreciate that Lyapunov theory is a very handy technique for nonlinear systems, both analysis and design. So, it makes sense to study that in somewhat fair detail of what is this Lyapunov theory and how do you make use of that in both analysis and design techniques actually. Next, we will discuss a very important recent concept which is called neuroadaptive design for nonlinear systems. That will be followed by some sort of application lecture which will discuss about how do we use all these advanced nonlinear control design techniques for aerospace applications, essentially these aircrafts and missiles again. And in this particular lecture, we will focus on dynamic inversion and neuroadaptive design. So, these are the two focus areas here, okay, this dynamic inversion and neuroadaptive design. Next, we will discuss backstepping design, just in one lecture will be sufficient to do that, and that is also a powerful robust nonlinear control design. So, it repeatedly uses this this Lyapunov theory in a loop structure which will give us some sort of a robust design, and that is what is backstepping design. Then we'll discuss about an overview of what is LQ, linear quadratic observer, and a very quick review of what is very commonly known as Kalman filtering. And then probably we'll also give you some sort of I'll try to give some sort of very quick overview of what is called as extended Kalman filtering, which is very useful in practice. So that is how it is structured, but towards the very end we'll discuss also one quick overview of what is called as nonlinear observer design also, not necessarily the extended Kalman filtering, but using Lyapunov theory and feedback linearization concepts like that, how do you come up with some sort of a nonlinear observer design. So that is how the entire course is kind of structured. So you will see all sort of starting from classical concepts, the overview, to review of matrix theory, Laplace transform, to transfer function, to linear design analysis, stability theory, controllability, observability, to pole placement, using both as control design and observer design. Next followed by this optimal control, LQR design sort of thing. Along with that, some flight dynamics and applications in aerospace engineering. And next we'll move on to nonlinear control design, where it discuss dynamic inversion, backstepping design, Lyapunov theory, and neuroadaptive design. And then again towards the end we'll discuss about something like linear quadratic observer, and then extending on to that to Kalman filter concepts, followed by some sort of nonlinear observer design. So it gives you, this entire course gives you some sort of overview of the spectrum of topics that we discuss in nonlinear and linear designs together. So that's how this syllabus is structured for this course. About references, you can see there are nice references available for linear control, and the first book is my first reference all the time. That's the normal, nice, very cleanly, very neatly written for good understanding. This is also a nice book written by Ogata some time back. And then some concepts of especially controllability, observability, LQR design and all, will take it from Friedland. And then there is also a nice book by Madan Gopal, who is a professor at IIT Delhi, about modern control systems theory. So some of you can essentially buy these books to get more depth knowledge here. About nonlinear control, my favorites are first two. The first is Marquez, which is nonlinear control system analysis and design, just published not too long back in 2003. And I also like this Slotin and Lee book very much, because it's also a engineering perspective. It doesn't give you too much of math details and all, but it gives you fair amount of math, but it has also engineering insights into that. So these two are my favorite books. And then there are support books which are available, which are written by Khalil and Isidori also. Especially nonlinear control systems should also include some sort of a current literature, which are not available in textbooks per se. Reference about some other topics, for example, optimal control will be taken from Bryson and Hu. There are some filtering like Kalman filter radius and all will be taken from Crasidis and Jenkins. There is a very neat Bible sort of book available here, which is Control System Handbook. Just about any topic you can have a quick overview by having this book. And then flight mechanics concepts and some review of flight control will be taken from Nelson, and some math concepts will be taken from other books as well, but primarily from Krasik. Okay. That's how it is. It's there. It's not an exhaustive list. There may be concepts from other books as well. So that's how these topics are selected from various places and put together actually. Now let's move on to lecture 1. Okay, that's an overview of the entire course. So the lecture 1 is introduction and motivation for advanced control design. That's the first thing that I like in any particular course. Before I study those material, what is the utility? What's the motivation? Why should I read that? I mean, that kind of idea. So let's have a quick overview of why do I need to study this concept. Okay. So concepts and definition first. So first we need to know what is a system, and any collection of interacting elements for which there are cause and effect relationships among the variables. So that's the formal definition of a system. So that means you have a collection of interacting elements, and there should be cause and effect relationship among those variables as well. Then only you talk about that as a system in general. Okay. And this particular subject we are more interested about dynamical systems, and that means that is a system in which variables are really time dependent. That means the variables really evolve with time, they do not remain constant per se. So, that is a dynamical system in philosophy sense. To study anything in that those direction, we really rely on this mathematical model, and this mathematical model is a description of a system in terms of mathematical equations. So, if you have a static system, then you really talk about algebraic equations. If you have a dynamical system, we take the help of differential equations, or in a limited sense transfer functions, either way. But transfer function representation is also an equivalent representation of differential equation form. So, that is how we really need a mathematical model before we analyze the system dynamics, whether you analyze or try to design a control or synthesize something, for both we need mathematical model actually. Then system variables, there are various types of variables, and first variable is what we call as input variables. And this input variables can be of two types, one can be of control input and the other one can be noise input. So, noise is also an input, I mean whether you like it or not. So, control input is essentially a set of manipulative variables, and they are usually known because they are computed precisely. We are the one who is computing that. So, we kind of know it what we are computing anyway. So, control variables are essentially the manipulative input variable that you really want to manipulate so that your system behaves nicely. However, the noise inputs are actually inputs, but they are usually non-manipulative, they do not obey us, and they are usually unknown. That means, you cannot talk about something that is known to me and that is a noise. I mean, that is, if you really know that, then that is no more a noise. Okay. If you know any input really, and you exactly know what is the value of that and things like that, then really that cannot be considered as a noise per se. Okay. So, that is how we kind of visualize that. So, we like to mainly deal with control inputs. Okay. However, we want to reject these noise inputs in general. I mean that is our motivation actually. Then the next set of variables are output variables, and these output variables are again of two types. One is sensor output and the next one is performance output. And again sensor outputs are something that are usually measured by sensors. We have a set of sensors which will keep on measuring these variables. So, those are sensor outputs. However, performance outputs are variables that govern the performance of the systems, and usually these sensor outputs and performance outputs need not be same. They can be same, then they can be different. For example, if you really want to land an aircraft, so the height becomes a performance variable. However, you may not have a direct measurement of the height of the vehicle. So, you can still measure your position of the vehicle, that is a different sensor anyway. So, you want to land, that means height is a performance variable, but height is not something that you are directly measuring. You can measure also, there are height sensors available anyway. Okay. That means, the variables may or may not be same. I mean that is a typical thing that we really need to remember that actually. Then the next set of important variables are state variables, and these are a set of variables that describe the system completely. That means, if you know the system states really, that means you know almost everything about the system, including what is going on internally, even though your sensors does not give you that. The sensor input can remain silent about that, but when you talk about states per se, that means you really know everything about the systems, because that is how the states either come from, let us say, physical relationships, for example, Newton's law or Kirchhoff's law like that, or they can come from system identification also. Okay. So, there are techniques available to know that, but the whole idea is once you know the state variables, we know almost the entire thing about the system. That is how it is, those variables they mean that. Next, about system study. So, when you talk about studying a dynamical system especially, then it can be classified into three parts. One is the model development, and next is once you have the model, that means a mathematical model which actually includes parameter identifications as well. So, essentially the laws of nature, what we know, like F equal to ma, that's a universal law. However, we really do not know that particular value of m for a particular system. So, that is the type of problem that you discuss about. Suppose you do not know the mass of the system, then can you really identify that from a sequence of measurements actually. Okay. So, that is the type of study which falls under parameter identification. It essentially falls under the broad spectrum of model development. Okay. But this particular system, I mean this particular study is beyond the scope of this course. So, in this particular course we will not discuss about that. However, we will assume a model that is known to us, okay, and then we will go into that next what is known as system analysis. So, once you have a good description of a model, and then next is to study that system, whether the system is really behaving nice way or not, before you do anything on that. So, that is the concept that we study about, let us say stability of the system, controllability of the system, observability, like that. Those are the analysis tools that we kind of take the help of, and then study the system behavior first. Okay. Next, once you study the system behavior, if it is doing well, okay, if the system is really performing well, then there is no need to do anything, we can just relax actually, and in that sense there is nothing much to do either. However, unfortunately most of the systems are not like that. So, there will be some issue or other, and then we really want to do some system synthesis. That means, we really want to do some sort of a control design. Essentially, we want to force the system to behave as we would like it to behave. Okay. So, that is our job to do that. So, in this particular course we will study both system analysis as well as system synthesis. In one particular lecture for that is like neuroadaptive design, we will partially address this issue. Okay. In other words, we will know the model to a good extent, but there will be some degree of unknown quantity in the model itself. Then can we really address that issue? So, there is a very loosely we will talk in one or two lectures about that little thing in this course also, but largely this particular course will be about system analysis and system synthesis. Okay. Next, we will have a simplified description of a control system. Then all of us probably know this that we can visualize this as a block diagram, and then in this block there are input which are essentially stimulus, and input again can be both control input as well as noise input, and then there are desired response, that is the performance output variables, how do you want them to behave, that is also you have to give that as an input to the system, then only the system will know what you really want to do. So, both of these are actually going as input to the control system, and as output you can talk about actual output, that is what is your system sensors give you, and this can be really performance output, that means how is your system is actually responding. Okay. So, that sense these are all sort of a overview that you can conceptually talk about. Then mostly we will discuss throughout the course we will need this response behavior sort of thing, and when you discuss or when you talk about dynamical system response, there are two parts essentially. One first is transient response and next is steady state response. So, steady state response is something that happens after some time, and transient response is something that happens initially. Okay. So, this part of the system response is transient response, and that part of the system response is actually steady state response. And in steady state there may be some error also, like whatever you want the system to go, you may not be exactly doing a 100% perfect job. So, that means there may be some steady state error, and in the transient response there may be, this is a typical transient response, does not mean every response is like that. There may be overshootings and then it may stabilize and things like that. We will see little more as we go along actually. Then there are concepts called open loop versus closed loop, and open loop system means you just give input to or a reference command to the system, and then just observe the system what it is doing. You are not really doing anything else more than that. So, you are just asking the system to do something, and then you have designed your your controller where you for an open loop system. Open loop controller means there is also a controller by the way, but that controller is designed a priori. That means you visualize all sort of scenarios that you are talking about, and considering those scenarios you actually design the control input a priori, but online there is no correction. So, that is the difference actually. So, you have some controller which is available to you, and then there will be disturbance coming here which is like a process noise, and then there will be sensor noise here. That is how they go into the system anyway. So, there are process noise, there are sensor noise, all sort of things will be there with you, but we will not be able to discuss that online. You will do everything offline. Okay. Then you take that controller and then just apply that. I mean, that is when whatever happens, it's not on our job anyway. So that's an open loop control system. But on contrary, there are closed loop systems. Closed loop system will have a feedback loop in between, which will take the sensor outputs. Well, they are noisy, but you still have some information there. So we will take that noise, noisy output or whatever, noise free output, whatever is available to us, and then, okay, I don't know. Then we'll use that that information, and then we'll have some sort of a error signal which will help us actually. There is a input or reference signal, and then what is really happening is going there as a feedback information, and that will give us some sort of a error signal, based on which we'll be able to correct the system behavior even further. Okay. So that's the difference between open loop and closed loop system. Next, we'll discuss about system classification per se. It's a different classification, for example. I mean, it's a different sense, we can we'll discuss about that. And first thing that comes to mind is whether you talk about a system as a lump parameter system or a distributed parameter system. So, lump parameter system is what we visualize is a single unity, the single entity, the entire system dynamics is considered, entire system is visualized as a single unit actually. In other words, there is no relative dynamics between different molecules of the system. That is the precise statement probably. Okay. That means if some molecule X moves, then every other molecule also moves by the same amount, same direction, all sort of things. That is a lump parameter system. Typical examples are like automobiles or aircrafts and missiles, all sort of things what we discuss. Normally, we visualize it as lump parameter systems. And there we really need a set of ordinary differential equations to describe the system dynamics completely. However, if you go a little more deep into that, there are systems which we cannot describe as lump parameter systems. For example, temperature control or flow control or vibration control, like that. There has to be some dynamics between different molecules of the system as time evolves. So, that means you really need some sort of a partial differential equation to describe these distributed parameter systems. So, there is a remarkable difference things, because here we talk independent variable as single independent variable, particularly time. But here you can have time as independent variable as well as some special variable as independent variable like time as well. Okay. So, here we will talk, in addition we also need to discuss about boundary conditions, whereas here we will need only initial conditions. In distributed parameter system, you need both initial condition and boundary conditions as well. Okay. Next, we can visualize systems from continuous time versus discrete time. So, whether the time variable, which is independent variable, that evolves in a very continuous manner, or it really evolves in a discrete sense. That means, the time signal just jumps from one value to other value actually. Okay. So, that is the type of system that we visualize as discrete time system. Otherwise, it's if the time is very continuous, smooth and all that, then we visualize that as continuous time system. Next, there is a similar visualization you can do from the dependent variable sense also. This is about independent variable. When you discuss about discretization of time, time is an independent variable anyway. Now, here you can discretize the dependent variable also or not. I mean, if you do not discretize the dependent variable, it is non-quantized, and if you really discretize the variable, then it is quantized. And one good example is probably our digital clock, digital watch. So, the time itself is discrete, but the position of the watch hand or whatever, that pointers and in the watch are fairly discrete. It jumps from one point to one point to one point actually. Okay. So, that is kind of a quantized description of the system. Next, we can classify the system from time invariant point of view as well as time varying point of view. That means, if the parameters of the system or the nature of the system dynamics do not change with time, that is actually time invariant. If it changes with time, that is time varying. Okay. Next, we can visualize that from linear versus nonlinear point of view. So, we can have linear system dynamics, or we can describe that as nonlinear system as well. That we'll discuss little more on that as we go along actually. So, here it is. So, we describe the linear system as systems that obey the principle of superposition essentially. And what is principle of superposition? There are two criterions. One is multiplying the inputs by any constant alpha must multiply the output by the same constant alpha. And next, the response of several inputs applied simultaneously must be the sum of the individual responses to each input applied separately. So, these are the two criterions that you really require here. Examples, there is a static system. If there is no dynamical system, but there is a static system in mind, then we can very well take this common example, what y equal to mx plus c, we all know that represents a equation for a straight line, and that equation for a straight line in general does not mean that represents a linear system. So, you can very clearly see, probably we will see that in next example also, that y equal to mx plus c is a linear system provided c is 0. If c is non-zero, it does not obey the principle of superposition actually. And okay, this particular thing I will demonstrate that through this example. So, let us first discuss about a linear system. So, x dot equal to 2x, okay, in a dynamical sense actually. Okay, so if we talk about dynamical system, let us talk about example 1, which is like x dot equal to 2x. Then you can very clearly see that if I multiply like let us say alpha times x dot, then alpha times 2x, I can substitute that. Okay. Then this particular thing, okay, this particular comes no, okay, anyway. So, this particular alpha times 2x, I can manipulate that like 2 times alpha x. So, essentially if I multiply the input by alpha, then the output is also getting multiplied by the same quantity. Okay. So, that is actually a linear system from first condition. Now, second condition also you can very easily verify that if you start from here and then go to this next step, then you can substitute that as 2x1 plus 2x2, then you can take 2 common, then you can see that okay, if I multiply that, if I add that essentially x1 plus x2, then the output is also similar actually. Okay. So, essentially x dot equal to 2x is a linear system in that sense, it satisfies both the principles actually. Now, about nonlinear system, let us take the very similar example, but we just add the quantity 3 here. Then what happens? If you just carry out the same algebra here, then here you will see that 2 does not multiply the entire thing. The 2 multiplies only this particular component, and hence it is really not satisfying the multiplicative criterion. Okay. Similarly, the addition criterion is also not getting satisfied, that you can very clearly see here. I start from here, dy dt of x1 plus x2, then I go to next one, x1 dot plus x2 dot, I substitute it, x dot equal to this 2x plus 3, that means x1 dot is 2x1 plus 3, x2 dot is 2x2 plus 3. However, it is not 2 whole into that x1 plus x2 plus 3, it's not going to be like that actually. Okay. So, that is where we fall apart actually. Okay. Anyway, so now next example also you see that x dot equal to 2 sin x, again it will not satisfy the conditions that we are looking for. It will not satisfy the condition of multiplicative property, and it will not satisfy the addition property either. Okay. So, that is how you can see that the first one is a linear system, okay, satisfy the principle of superposition, whereas the next two are really not linear systems actually. So, then okay, that is how it is. Then how about this nonlinear system? So, by definition what it means, the nonlinear systems are essentially systems that are not necessarily linear, that is a precise definition. So, by nonlinear system we really we really do not mean that it is actually a not linear system, it is actually a not necessarily linear system. That means, all linear systems are part of the nonlinear systems also, but not necessarily vice versa. Okay, that is the definition actually. Now, how about analogous systems? Analogous systems are systems having the same mathematical form of the model. That means, if you really discuss about two analogous systems, you take the system dynamics for system 1 and system dynamics for system 2, mathematical they are identical, they will not be very different either. But the variables for system 1 may mean something and variables for system 2 may mean something else actually. So, that means, suppose for example, spring mass damper system and RLC system are really analogous. One is a mechanical system, another is electrical system really. but they are the meanings are different, but the mathematical description of the system dynamics will remain same. And that actually these kind of ideas actually essentially gives us the flexibility to discuss concepts in a generic way. We do not have to discuss about very specific particular discipline per se. Okay. Next, let us know little more about nonlinear versus linear systems. And first of all, we all know probably that nonlinear systems are more realistic, whereas linear systems are only approximation to reality. We know that. And second, the nonlinear systems are usually difficult to analyze and design. Okay. However, there are linear systems design technique or analysis techniques, there are many tools available. So, they usually become simpler to analyze and design. Okay. There are many tools which are well developed for linear systems, whereas it is not very much well developed for nonlinear systems. There are many tools that are available, but still there are many issues that people are doing research on. So, tools are still under development for nonlinear systems. Okay, these are the first three are philosophical differences. Now, let us discuss more about very precisely quantitatively what are the differences that they come in actually. About linear systems, the very great thing about linear system is it can have only single equilibrium point. That means, for linear system we cannot have really multiple equilibrium points. Whereas, for nonlinear systems, the very fundamental difference is it can have really different multiple equilibrium points. Okay. Let us well you can see that in a example sense. Okay. If you really let us discuss about something like x dot equal to let us say x minus let us say x cube. It is a very standard example anyway. So, if you really talk about equilibrium point or linearization of this system will be something like x dot equal to x, about x equal to 0. Now, here if you really discuss about equilibrium, I put it to 0, then the only solution is x equal to 0. So, that is the only equilibrium point I can have here. And this is actually not a very different system than the original system, what you started with. However, if you really talk about nonlinear system equilibrium, then this will be 0. If I put that gives me a nonlinear equation to solve, and then I get the solution as both 0, okay, because this is actually x into 1 minus x square. So, this is 0 as well as plus or minus 1. Okay. So, here I have only one equilibrium point, okay, and here you have really 3 equilibrium points. Okay. So, that is how these nonlinear systems are really different from this actually, from the linear systems. Anyway, next is the system stability nature, what we discuss here. Not only they have multiple equilibrium points, but the system stability nature can depend on the initial condition as well, where you start with, whether your system trajectory will remain stable after the starting point or not actually. That is also a concern for nonlinear systems, where that really does not happen for linear system. For essentially that is a very great behavior of linear systems, which essentially tells us that stability nature of the linear system is independent of initial condition, and that probably justifies the transfer function approach, where we typically assume 0 initial conditions everywhere, which we start with a differential equation and then you proceed next step for Laplace transform and all. Very typical, we will assume 0 initial conditions for all system variable and their derivatives. So, this is the reason why we really do that, because the system stability nature is actually independent of initial conditions. So, we put 0 to make our life simpler and then proceed further. But same thing we cannot do for nonlinear system, because nonlinear system stability behavior depends on the initial condition. Okay, so that's the difference actually. Okay, next, in nonlinear system we have some concepts called limit cycle, and linear systems we really don't have either limit cycle, there is no bifurcation and no chaos. So, these are all simplicity for linear systems, whereas we have the limit cycle, bifurcation and chaos for nonlinear systems actually. So, let us discuss one by one. So, what you mean by limit cycle is something like self sustained oscillation. That means, if you go to that example, if you discuss about this limit cycle behavior, it is a self sustained oscillation. So, let us discuss about what is that. if you draw something like a phase plot, that means x versus x dot, this is x dot, okay, then essentially it will have some sort of a closed plot actually. That means the trajectory can keep on moving around that. Okay, that means it can start from some point, but it will never go to 0. This is let us say 0 0, but it will never go out or it will never come back to 0 either. So, that means it will keep on the trajectory. If you see, it will exchange energy between x and x dot. However, it will keep on moving along the same path, need not be very circular, but can be some sort of a closed path actually, closed curve. And the typical example is van der Waals oscillator. So, van der Waals oscillator will typically give us this kind of a trajectory. And there are flutter problems in aerospace engineering, where the wing of the aircrafts, they derive energy from the outstream, then they keep on vibrating in while they are flying actually. That is a typical problem of nonlinear systems. Now, next bifurcation, and what is bifurcation is essentially the number of equilibrium, I don't know. Okay, so the number of equilibrium point, they and the stability nature, they can vary with the parameter values. Okay, that means initially you can have just initially you can have just let us say one equilibrium point, but as the parameters vary for the system, then the number of equilibrium points can really vary as well. Let us go to that same example where I will be able to demonstrate you a little more. We are discussing about system dynamics. Let us talk about x dot equal to x minus, let us say alpha x q again, and alpha is really small. Okay, let us say alpha, if you discuss like that, let us say time versus alpha of t, then it starts with a very small value, it stays like that, and then suddenly it starts going up actually. That is very possibility anyway. So, when alpha is small, typically we neglect that, and then we tell, okay, that is our approximate system here. So, it roughly behaves like a linear system. Okay. But when alpha starts moving up, alpha is more and more, we cannot do that. So, we will go back to that and then tell, okay, initially my equilibrium point was x equal to 0 anyway. So, if I put this is 0, that is equal to x, my one equilibrium point. But when I go back to that and talk about 0 is equal to x minus alpha x q, then essentially it has given me again, depending on alpha, it is really the solution will be like that, 1 minus alpha x square. Okay. So, the equilibrium points are both 0 as well as something like plus or minus square root of 1 by alpha sort of thing. You can very clearly see from this equation really. Okay. So, when I cannot really neglect this alpha, then the equilibrium points start showing up. Initially it was only 1, later it will start showing up actually. Okay. So, in other words, suppose that is not the system. Let us say your system was something like x dot equal to like let us say alpha x minus x q. Okay, this something the parameter being there. Then the equation will be something like 0 into like x into alpha minus x square sort of thing, and then your equilibrium point will be 0 and plus or minus square root of alpha really, not 1 over alpha. Then what happens when alpha goes on increasing, then your xe, if you plot xe versus time, okay, initially it was 0 0 0, suddenly it will going up and all that actually. Okay, so there will be 3 equilibrium points later. So, this kind of bifurcation behavior is something called pitch fork bifurcation. Okay, it's like some sort of a fork kind of idea which is coming actually. Okay. So, these are the concepts that are useful for nonlinear systems. That's typically not the case for linear system. Next is chaos. Chaos is like for very small difference in initial condition can lead to large difference in output as time increases. So, what is that? Suppose you have something like a system response, and suppose it is like this, then the initial condition is very close, then you expect the system trajectory to follow that very close. But normally, I mean for chaotic system, it remains close for little time and then it will be very different after that. And typical examples are weather forecasting system. Weather models are typically chaos models. So, initially your prediction will be good. So, whether the weather prediction for a day or half a day is normally okay, but weather prediction for a week is typically erroneous. That's primarily because they are the truncation error of computation, what they forecast, they use the model to forecast and all that, they will dominate after some time. very quickly rather, and then we will have problem about wrong prediction later. Okay. So, that is the behavior of this chaotic system. So, we will be able to do that in a very little time, we are okay, we are correct, but then in a long run we are not okay actually. Okay. Those are typically chaotic systems. Next, last one, like the frequency and amplitude can be coupled here. Okay. And in this nonlinear system, it can be coupled. Typically, what we visualize in linear systems, they are decoupled. The frequency is one aspect and amplitude is another aspect in a signal. But here they can become really dependent, and there are some analysis tools which will really analyze that in a coupled manner, describing function analysis especially. Okay. Okay, let us keep that. Next, let us quickly compare some sort of classical versus modern control. Classical control was developed in 20s to 50s, primarily between First World War and Second World War, and model control was developed mainly. And here what we mean by modern control is linear control essentially. So, they are developed between 50 to 80. There are still under developments, many concepts and all, still not completely over per se, but majority part of the development happened during 50s to 80s. Then here the necessary tools are frequency domain analysis. So, essentially transfer function based. Here we necessarily talk about differential equations based directly in the time domain. Here we discuss about single input single output models primarily, even though it is MIMO system, we discuss that as single input to single output somewhere, and then we take that relationship into account, and then we visualize that as a single input single output system at a time. But in modern control there is MIMO models and we manipulate those models directly. Okay. And this one deals with input and output variables only, the classical control systems. Whereas the modern control systems, it will deal with both input, output and state variables as well. Okay, it does not stop at input and output only. Here, but the good thing about linear classical control system is some sort of well developed robustness concepts about gain and phase margin like that. These are all robustness concepts nicely well developed. It is not fairly well developed here, but there are a lot of effort going on nowadays to develop equivalent concepts of robustness from modern control point of view. There are, and even people now discuss about adaptive control point of view, how do you come up with criterions for robustness and all that. Okay. So, there are many research topics, there are many active people who are doing research on these lines and all that. Then another drawback of classical control is essentially there is no controllability, observability inference directly from the system model. Okay. Because it fairly remains silent about the state model, but if you state variable, it does not talk anything about that. So, that information remains hidden there actually. But if you have a model that is completely have a transfer function that completely describes the system, then you can create a some sort of a MIMO model out of that. There are equivalent transformations available from transfer function to time domain and all that. Then the inference turns out to be like this, that there should not be any pole zero cancellation for this, for both observability and controllability. So, these are inferences there available in a loose sense and all that, but it is not very tight sense, they are not available here. Another drawback is no optimality concerns, it all talks about stability only. Okay, whether the closed loop system will remain stable or not, that is the only concern that you have. But in modern control, we really talk about optimality issues can be directly incorporated. That is how we discuss about optimal control design techniques. And these are well developed and very much used in industry, whereas these are fairly well developed and slowly gaining popularity in industry as well actually. There are ideas of merging these two, which is actually linear robust control design ideas there. And some lessons to remember before we proceed further, that the feedback is always there whether you like it or not, and we have to make use of that. There are some lessons to remember. This is a nice article by Bernstein, and you can see that the feedback is pervasive actually. Then also we need to remember that block diagrams are not necessarily circuit diagrams. That means the block diagrams that we discuss in control system or system analysis tools and all that are essentially conceptual ideas put together in a structured way. It has absolutely no connection with circuit diagrams. There can be connections if you discuss about electrical systems per se, but in general block diagrams are actually conceptual ideas put together. Then next thing what you do, given a system, you find out the equilibrium points and linearize if necessary about that. Next thing, check stability. Then assure nominal stability. That means if you assume the transfer function is very correct, there is no error or there is no parameter inaccuracy like that, then the only concern that you have there at that point of time is assume stability for the nominal system. That is the first condition. Next, you have to kind of make sure that there is a robust stability. That means after stability, you have to discuss about robustness issues actually. Normally those are difficult to obtain, but robustness is a must for any practical control system, for any practical use. So essentially after stability, that means after both nominal and robust stability, then you have to worry about what is the performance behavior. Okay. So without compromising too much on these aspects, especially like nominal stability, there should be no compromise at all. Robust stability, you may like to compromise a little bit because these two are really counteracting with each other anyway. But without compromising too much, you can discuss about performance of the system also. So that's another system. Now typically we like to use high control, but high control gains has good benefits as well as bad benefits, bad effects and all that. Good benefits is it leads to some sort of robustness behavior, it gives you robustness actually, so it assures good tracking also. However, the bad effect it leads to control saturation, it leads to noise amplification like that actually. So you have to be careful about selecting a gain properly. Now we have to also see that we have to be worried about these lightly damped poles because they cannot be rejected so easily. Okay, the behavior of those lightly damped poles are long term effects actually. So these are and they are also, remember, they are like close to imaginary axis. That means what happens is there is a danger that these poles may go to the eta plane and the system becomes unstable after that. So you have to be very careful about these lightly damped poles which are close to the imaginary axis actually. Now time delays can be deadly, so we worry about that. The very good part of it in this article I found is this part. What we have to do is respect the unstable mode. If there is one unstable mode somewhere, it is going to couple with others and pull everybody into instability. So neglecting whatever amount of unstable mode wherever it is not a good idea. So little down the line it will be devastating actually. Non-linearities are always present. That means we have to live with non-linearities. And how do we handle that? Whether in approximate sense or true sense, that's our way of looking at the system. And last, you can also remember that people's lives and or our country's pride may be at stake. If you talk about good missile systems, for example, strategic missiles, mostly, okay, I hope there will not be any use in the future for that, but that's the country's pride. Sending somebody to moon is country's pride. Okay, they may or may not get gain in a monetary sense in a long run, but that's a country's pride. You demonstrate capability actually. But if you really develop a 500-seater aircraft and then you put it into danger, there are people's lives involved in that. So both are kind of important to us. So in summary, benefits of advanced control theory, we discuss about MIMO concept, multiple input, multiple output. Then there are lesser assumptions involved and lesser approximations. And next we will be able to do simultaneous disturbance of rejection and command following both together. We will be able to do robustness in presence of parameter variations, external disturbance, all sort of unmodeled dynamics, etc. There are concepts of fault tolerance, self autonomy, things like that. And next we will be able to discuss about optimality of the controller. That means we will be able to incorporate optimal issues right away, which will lead to variety of advantages like minimum cost, maximum efficiency, non-conservative design, etc. like that. There are many things we will be able to discuss here. And then we will also be able to use these trajectory planning issues, which are typically concerns of outer loops, that can be incorporated into the control design also. Those are concepts called integrated guidance and control, typically in aerospace. So even before that, we will be able to discuss what is my optimal path to follow. That means the trajectory optimization, which is typically carried offline normally, that also can be discussed directly in the framework of control systems theory. Okay. So that is a great advantage of advanced control. Then state and control bounds can be incorporated. You don't have to live with whatever is coming. You know the bounds a priori. Then accounting for those bounds, we will be able to design a control system based on those bounds, because we know that information a priori. So we will be able to use that actually. Okay. And next, integrated designs, what I just discussed a couple of minutes back, that generally in traditional sense will have some outer loop, then followed by inner loop and things like that, but you can eliminate that in some sort of integrated design, which will lead to some sort of better performance altogether for the overall system actually. Then why nonlinear control for particular, not necessarily linear system theory. First of all, it improvements of existing control systems. So, neglected physics can be accounted for. The nonlinear system, we are not really linearizing the system dynamics around anything. So, any operating point. So, you can discuss about improvement of the existing linear controller. There is a linear controller, you want to improve the performance there. So, you now account for nonlinearities that you neglected before and you try to improve on that. That is one aspect of nonlinear control design. Next, explicit account of hard nonlinearities and strong nonlinearities can be there. So, and what is hard nonlinearities? These are discontinuity in derivatives. That means saturation, dead zone, hysteresis, all sort of things. Those are hard nonlinearities. Strong nonlinearities are essentially, you cannot neglect these higher order terms in Taylor series. They are smooth signals, but there are strong, there are large components from higher order terms as well. So, we cannot neglect that at all. So, but in both sense we will be able to discuss for nonlinear control, and in this particular course we will give importance towards emphasis towards strong nonlinearities. Hard nonlinearities we will not discuss too much on this course actually. Next, we can directly deal with model uncertainties, okay, and there are something unknown about the model, we will be able to incorporate that. Next, there is a big advantage of discussing about nonlinear control, and in some cases it actually leads to design simplicity over the linear system, which is slightly counterintuitive, but as we go along we will see some nonlinear design things are actually simpler than linear design techniques, and one example is dynamic inversion per se. That comes to mind is essentially the feedback linearization or dynamic inversion essentially eliminates the gain scheduling philosophy, and hence it is simpler than the linear design technique per se. Okay. Okay. Next is it can also lead to cost and performance optimality. So, if you really talk about optimal control design for the nonlinear system, it is not optimal controller for the approximate plant, it is actually optimal for the true plant. So, that is how it can lead better cost and performance optimality for the true plant. Then techniques of nonlinear control design, there are many techniques available. One is the phase plane analysis, next is Lyapunov theory, then is the differential geometry, which is essentially feedback linearization or dynamic inversion. Then there are intelligent control techniques which are based on neural networks, fuzzy logic, genetic algorithms like that. And there are earlier ideas which are like describing function analysis, which is like amplitude and frequency getting coupled, that kind of ideas there. There are optimization theory based ideas, which is variational optimization, dynamic programming like that. And for about all that, we will not discuss everything in this course. We will be discussing some sort of overview of phase plane analysis, Lyapunov theory, differential geometry, but intelligent techniques we will limit ourselves to little bit on neural networks. And then optimization theories we will also be able to talk a little. This is some sort of an overview, and then there are some applications of aerospace engineering, that is how we discuss all that. Essentially, it is like some variety of applications for missile guidance and control. There are aircraft flight control, there are guidance and control of UAVs essentially. So, all these actually I have listed out here many different things like various command following, you can discuss about reconfigurable control, you can discuss about eliminating gain scheduling and all sort of things. So, these are all applications of this. So, that is all about this particular lecture. Thanks a lot for the attention.